I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, number 47, we will see the causal networks in probabilistic reasoning. Once again, I welcome to this session on causal networks in probabilistic reasoning, where we explore the fascinating intersection of probability theory and causal inference through the lens of Bayesian networks. In today's interconnected world, understanding how variables influence one another under uncertainty is crucial for intelligent decision making. Causal networks provide a powerful framework for modeling these cause and effect relationships, enabling us to make informed predictions, diagnosis, and strategic choices across diverse domains, from healthcare to artificial intelligence. This session will guide you through the foundational concepts and the practical applications of causal reasoning and the equipping you with the tools to uncover hidden dependencies and reason effectively in uncertain environments. And this causal network in probabilistic reasoning, particularly within Bayesian networks, offer a structured approach to understanding and modeling cause and effect relationship among variables under uncertainty. These networks use DAC. DAC, we have seen it in the previous lecture. DAC mean directed acyclic graphs. DAG. So these networks use directed acyclic graphs where nodes represents variables and edges denote causal influences, allowing for intuitive and computationally efficient reasoning. By incorporating conditional dependencies, Bayesian networks help infer the likelihood of outcomes based on observed evidence, making them powerful tools in decision making, diagnostics, and prediction. Understanding these causal relationships enhances the interpretability of probabilistic models and support more accurate and explainable AI systems. Say, for example, if you are taking the medical diagnostic variables, here we will write it as medical diagnosis, disease to symptoms. Based on the symptoms, we can identify the diseaser, or otherwise we can if you know the symptoms, we can say what type of disease would be. A Bayesian network can model how a disease, if you are taking flu, the disease flu cause certain symptoms, what are all the symptoms it will be causing, like fever and cough, etc. If a patient reports a fever and cough, the network can infer the probability of the flu being the cause. Flu being the, we can write, we can say this flu being the cause. Causal relationship, we can, how we are going to write the causal relationship means flu, fever comes. Otherwise, flu is there, cough, you may be affected with the cough. So in this way, we can predict. So many examples are there. Similarly, weather prediction variables, cloudy. If it is a cloudy, rain may come. Rain comes, wet grasses. If it is cloudy, there is a higher chances of rain, and it rains, the grasses becomes wet. Even if you only observe wet grass, you can reason back to the likelihood of rain. Cause saying is cloudy. How we can write cloudy, rain, wet grass. Similarly, examples, students' performances based on the scores, we can say exam score. Cause and relationship, we'll write it as study hours. Based on the study hours, understanding will be there. More understanding will be there. The understanding improves and which increases the chances of scoring high in the examinations. First, we'll see what is the causal network. Causal networks are probabilistic graphical models and representing the cause and effect relationship. That means causal networks provide a structured way to analyze the relationship between different variables in a system. Unlike simple correlations, they capture the directional influences that one variable exerts on another, helping in decision making and prediction. And these networks, they use, as I've said previously, directed acyclic graphs, DAX. We can call it as a DAX to model dependencies between the variable. This means what? A DAG is a graph, a graphical structure where nodes represents variables and directed edges indicate causations. The absence of cycles ensures that no variable can cause itself, making the model interpretable and logical. And the third part is unlike a standard Bayesian network, causal networks explicitly model interventions and counterfactuals. That means while Bayesian networks help in probability estimation based on observed data, causal networks allow us to intervene in the system. That is, example, applying a treatment and predict outcomes even when such actions were not previously observed. And what is the structure of the causal network? As I've said, nodes represents the variable. So if you are taking the example of disease, symptoms, and treatment, in this the node represents the variables. Each node in a causal network corresponds to a specific variable, such as medical conditions in a health model or financial indicators in an economic model. This structure helps organize and quantify relationship. Directed edges here, directed edges indicate causal influence. That means smoking. If the person is smoking, he may be affected with the, he may be lung cancer. The directed arrows here, this arrows shows which variable influence other. For example, smoking increases the risk of lung cancer, and this cause effect relationship is visually represented with the arrow. And next, conditional probability tables, CPTs. Conditional probability tables defines dependencies quantitatively. CPTs assign numerical probabilities to the relationship between variables. For instance, if smoking increases the likelihood of lung cancer by 30%, this probability is encoded in the table. And the next one is the condition dependencies for conditional independence in the causal networks. Conditional independence in the causal networks. How we are going to define a variables is conditionally independent of the other given in the in its parents. This means that once we account for a variable's direct causes, other background informations become redundant. For example, knowing that a person smokes might make genetic predisposition less relevant in predicting the lung cancer, and it reducing complexity in probabilistic reasoning. By focusing only on relevant dependencies, causal networks avoid unnecessary calculations, making them efficient for reasoning and decision making in complex systems. And if you are taking the example, if we know a person smokes, genetic disposition may not significantly change the probability of lung cancer. If smoking is a strong predictor of lung cancer, additional knowledge about a person's genetic risk may not significantly alter the probability. This simplifies the reasoning process. Next, causal inference and do calculations. Do calculus helps simulate interventions in causal models. Traditionally, probability calculations rely on passive observations, but do calculus allows us to model active interventions such as simulating the effects of new drug before administering it. Unlike a standard probability inference, interventions modify causal mechanisms. Normal probability calculations tell us how likely something is given past data, while causal inference tells us how changing one factor, like banning smoking and would alter outcomes like lung cancer rates. Example here, the studying the effects of new drug by setting treatment given do, we'll write it as given do treatment. Instead of just observing patients, we took a drug We can model the effect as if we assign the drug to random individuals, helping in clinical decision making. Next, counterfactual reasoning in causal reasoning. And here helps what if questions. In this case, if you are counterfactual reasoning allows us to explore hypothetical scenarios such as predicting whether a student would have passed an exam if they had studied more. They're asking questions. Example, what if the patient had taken the treatment? If a patient did not receive a certain treatment and the conditions worsened, and counterfactual reasoning helps estimate whether their condition would have improved had they have taken it, and useful for policy analysis, legal reasoning, and medical diagnosis. And counterfactual helps policymakers assess past decisions, assist courts in determining liability, and enable doctors to evaluate alternative treatment. Next, applications of causal networks, medical diagnosis, predicting diseases progression and treatment effects. Doctors use causal networks to determine how diseases develop and how different treatments impact patient outcomes, allowing for more effective healthcare decisions. Economic and policy, in this case, evaluating the impact of policy changes. That means what? Policymakers rely on causal models to assess how laws and regulations affect employment, inflation, or public health. And next, AI enhancing explainability in models. Machine learning systems use causal reasoning to provide more interpretable predictions, making AI decisions more transparent. Next, in the robotics, decision making in uncertain environments. Autonomous systems like self driving cars use causal networks to predict how different actions, example, braking versus accelerating, will influence outcomes. And the example, if you are taking smoking and lung cancer, notes. Notes, we will take it as smoking and lung cancer and coughing. And edges, in this example, three variables consider whether the person smokes, whether they develop lung cancer, and whether they experience coughing. Edges are S to C, C to D. This causal structure shows that smoking increases the risk of lung cancer, which in turn causes coughing. Using do calculus, what happens if we intervene and makes S is equal to 0? That is a non-smoker. If we force S is equal to 0 means non-smoker. If we force S is equal to 0, eliminate smoking, we can estimate how lung cancer rates would change even without historical data or non-smokers. Challenging in causal networks. We are facing some challenges also. Identifying true causal relationship versus correlations. Just because two variables are related does not mean one causes the other. For example, ice cream sales and drowning deaths both increases in summer, but ice cream does not cause drowning. Data limitations and biases. Incomplete and biased data can lead to incorrect causal conclusions. For example, a study on the effects of a drug may not be valid if it is only included healthy individuals. Computational complexity in large networks. Analyzing computational system with many independent variables requires significant computational resources and ethical considerations in interventions. Intervening in real-world systems such as imposing new medical treatments or policies must be done carefully to avoid unintended consequences. And coming into the conclusion, causal networks enhance probability reasoning by modeling cause and effects. By structuring relationship between variables, causal networks improve our ability to make predictions and take informed actions. They enable intervention, analysis, and counterfactual reasoning. These networks go beyond traditional statistics by allowing us to model interventions and explore alternative realities. It is widely used in medicine. It is widely used in medicine, AI, economics, and decision making. Their applications span multiple domains from diagnosing diseases to improving AI transparently. Future research directions in this case, what it means, it improves the accuracy and efficiency in large scale models. Advances in causal advances in causal modeling aims to handle large data sets, improve computational efficiency, and integrate machine learning techniques. Hope everyone understood this topic of causal inferences. Uh, this is very interesting topic. This is the advanced version of this Bayesian network. If you understand the concepts, you can solve any type of problem. The remaining things we'll discuss in the next section. Thank you.